Okay, so the main reason why I got into this proof system is to actually to explain one deduction rule which is of interest, and that rule is what is called resolution. Okay, it's an inference rule which is used for clauses. So basically, you apply it for CNF formula in CNF. It says the following: suppose you have two clauses phi1 and phi2, and you have proposition P. If you have a formula of the form, if you have already derived a formula of the form P or uh, C1, phi1, and you have a formula of the form not P or phi2, then this rule says you can conclude phi1 or phi2. Okay. So just to give you a short justification of this rule, right? Why it kind of preserves validity. Suppose so you look at this formula, the subformula, the first one, and suppose P does not hold, then for this is a disjunction, right? So if P does not hold, then for the disjunction to hold, then phi1 has to hold, right? Now if now look at the second formula, and now suppose that P does hold. Since this is again a disjunction, for if P holds, then for this formula to hold, then phi2 has to hold, right? So that means that irrespective of the status of P, we can conclude that phi1 or phi2 holds, right? So that's basically what this resolution rule says. Now, what is interesting about this resolution rule is the following fact that it is a sound and complete proof procedure for checking satisfiability or unsatisfiability, really, right? So that means that so it's a proof procedure, which means that you're not really using the semantics. It's just a syntactic symbol manipulation. What you can do is you can use this one rule. It's just this one rule to do a sequence of derivations. And if you're able to derive the empty clause, then you can conclude that the formula that you started with is unsatisfiable. Or if you end up with just pure literals and you are not able to apply this rule any further, then you can conclude that the formula is satisfiable. Okay, so you can show that this one rule is basically sound and complete for satisfiability. Yeah, of course, the drawback is in general it's not computationally feasible to use resolution as a complete procedure, it is sound and complete. Okay, and the reason why I wanted to mention this is, satisfiability, at least the way we looked at it earlier, was a semantic notion, right? But now what I'm saying is there is this one rule which is by which you can kind of solve satisfiability problem syntactically, right? So it's just simple manipulation. You're not using any semantics, and it gives you an answer to the satisfiability problem. Okay, so all these SAT solvers. So I won't get into the details of this resolution. I mean, the procedure itself is not very difficult, but for the sake of time, I'll skip it. So these are the two references you can take a look at. Again, I'll share these notes. So this paper is what usually defines this procedure, but it's a very good interpretation or a very good presentation of this entire procedure is given in this book by Ben-Ari. So it might make sense to take a look at this book rather than this paper. One way, so what this says is one way of solving the satisfiability problem is to simply use syntactic transformations, right, given by this resolution rule. And it is sound and complete. So you're guaranteed that you will be able to solve the satisfiability problem. Of course, in the worst case, it's not efficient, right? So that's what it says. So if you look at any of these SAT solvers, so basically what these SAT solvers are doing is defining a series of transformations, transformations of this formula which preserves satisfiability. Okay. Now the way you transform it involves a lot of heuristics to make it fast, but basically it's a sequence of transformations, and then you apply all these heuristics to kind of solve this satisfiability problem. So the resolution itself, I mean, it's a proof rule. So combining this proof rule with a search procedure gives you an answer to the satisfiability problem. So that's the insight here. Okay.
Hello.
Yes.
What does pure literal mean?
Can you repeat? Sorry.
What does pure literal mean?
It's just a proposition or its negation, right? So once you have that, you cannot apply this rule anymore.
Sorry, like I don't understand. What is the difference between this and a normal CNS?
No, it's an inference rule which is applied on clauses. So by pure literals, I mean just propositions and its negation. Okay, so forget about this mention of pure literals. Think of it this way: you keep applying this rule. If you are able to derive bottom, then you can conclude that the proper formula is unsatisfiable. If you reach a step by which you cannot progress any further, right? So you cannot apply a resolution rule any further, then you can conclude the formula is satisfiable. So that's one way of thinking about it.
Okay, okay, that
Yeah,
makes sense. Thank you.
yeah, yeah. Okay. Okay, so satisfiability is inherently hard. Propositional satisfiability. I said that for 3-sat is already hard, even if you restrict it to 3 literals in each clause. There are a couple of subclasses where it is efficient, and one is 2-sat. If you restrict the number of literals in each clause to 2, then you have a polynomial time procedure to solve satisfiability. And the other is what is called, you can define another syntactic restriction of the logic, and these are called horn clauses. These are the two main restrictions where it's interesting to know that satisfiability is propositional, is polynomial time. Again, I won't define horn clauses, but you can find a description of horn clauses and the procedure in this book again, right? So at the end of the session, I'll give you some references which you can which you can look at for more details of what I'm describing. Okay, so this is basically what I wanted to discuss about propositional logic, the computational aspects, and this notion of reduction and inference procedures. Any questions? Okay. So propositional logic basically acts as a foundation. Now, in many of the real world systems, you're not really doing Boolean reasoning. There is, well, up to a level you can do abstraction, but you need some more power, right? So you need slightly more sophisticated constructs. You have variables, you have values for variables, you're looking at comparison between values of variables, you're looking at arithmetic, right? So you have, in general, you have, well, functions, you have predicates and so on, right? And it may not always be possible to genuinely or honestly abstract it out into Boolean formalism. Okay, so what would be an extension, or what would be the next step? What would be a nice logical formalism to kind of reason about these more sophisticated systems, right? And the natural extension which you would want to look at is what is called first order logic or predicate logic. Okay. So this involves, so again, I'll try to give a formal presentation of the syntax of the logic. Just like in propositional logic, you have a bunch of logical connectives, right? So you have these logical connectives. These are the same that you have in propositional logic. So instead of propositions, you have what are called variables. Okay, variables can take values, need not always be Boolean values, right? So you have variables. These can take values, which can be more sophisticated than just Boolean values. And you also have what are called quantifiers. These are also logical connectives in first order logic. Okay. I'll come back to the interpretation of these things in a minute. So you have a bunch of logical symbols, which are the Boolean connectives, you have variables, and you have quantifiers. So these are your logical symbols. And in addition to that, this is where the real attraction of first order logic comes. You have a bunch of parameters, right? So parameters can be predicates. These can be relation symbols. It can be constant symbols. It can be function symbols. It can be equality and so on. Okay, so these are the typical kind of parameters that you have. So in propositional logic, you basically have propositions and Boolean connectives. Now you kind of enrich the language to basically include parameters, and that's really the difference, right? You also have these additional logical operators of operations of quantification, which is coming. All right. So that's basically the idea behind the first order logic. Okay. Now to formally define it, we have to get into a bit of details. So let me try to make it as simple as possible, right? So, but if you have any questions, please ask. Okay. So what I'm going to do first is define the syntax. Okay, so this has nothing to do with the interpretation of the logic. Again, it's like a set of rules. When do you say that a formula is well formed? Okay, so that's what I'm trying to define first. Now, this definition is slightly more complicated than in the case of propositional logic because you have all these objects, all these parameters, right? So the first thing that you want to do is fix what is called a language, a first order language. So these are a bunch of symbols. So the language in the case of propositional logic was just the basic proposition. So it was very simple. Now you have these parameters, you have relations, you have functions, you can have constants. So you need to fix the set of symbols that you would use for these objects. Okay, so that is what is done by a first order language. So what is a first order language? It consists of three sets: R, F, and C. These are very simple objects. So R is a set, and so it's just a set of symbols, just as in the case of propositions. The way you would want to interpret these symbols these are the relation symbols, right? F is also a set. The way you would want to interpret the symbols in the set is that these are function symbols. And you have C, which is a set of constant symbols. All right. Okay. Now, so these are just symbols. It doesn't have any interpretation. So R1, for instance, doesn't have any interpretation of a relation. It's just a symbol. So we use R1 to denote some relation. Okay, so at the moment it's just syntactic. R1 means it's a symbol used to denote some relation. F1 is a symbol used to denote some function. But what is that function? Well, there's no interpretation, right? It's just a symbol. Now, relations and functions typically have some kind of an arity associated with it, right? So if you have a function f, you want to know, well, in order to apply that function, you need to know how many arguments that function takes, right? That's what is called arity. Okay, so with each symbol, you also need to specify the arity of that symbol, and that is done by, so that is kind of built in to the language, right? And this is the typical notation that you use. This hash of R or hash of F, it denotes the arity of the function or the relation, right? So a simple example would be if you take a graph and you're looking at the edge relation, so you can now directly encode the edge relation as a parameter in the logic, right? The edge relation is a binary relation because it connects two vertices, right? So it's a binary relation. Okay. So a first order language basically defines the building blocks of parameters. Fine. And you have a bunch of variables. So these can take values, of course. And so you have a set which consists of a bunch of variable symbols. All right. So all these are countable sets. Okay. So that's what is so this forms the building block of the logic. Any questions? So okay, so let me just give you some examples, and then if there are questions you can ask. Examples of first order language, for instance, propositional logic, right? This is an example of a first order language. What are the relation symbols? You have these propositions which are relation symbols, and the arity is 0. Right? If you take a relation symbol with arity 0, it's basically proposition. It's either true or false. Right? Do you have constant symbols? Of course, no. Do you have function symbols? No. And do you have equality? The notion of equality? No. Right? So you only have relation symbols of arity 0. That is what is propositional logic. Right? Of course, and so this is the language, right? I'm not talking about the quantification that, of course, you don't have, but in terms of the FO language itself, this is how you would define propositional logic, right? What about set theory, the basic set theory? You would have a relation symbol, which is the element of, right? So this would be a relation symbol, and you would have a constant, which is the empty set. This is a constant. Are there function symbols? Well, you don't really need function symbols. So no, you don't need function symbols. Equality, typically, yes, you would have equality. Okay, so that's set theory. And elementary number theory. Well, you can have a relation symbol, which is this less than. You can have constant, which is, let's say, a 0. And typically, you have these function symbols, which is successor of a number, addition, multiplication, and equality, you would have equality. Okay, so these are examples of first order languages. Fine. So again, I'm not talking about the interpretation of these symbols. It's just that I'm specifying what are the symbols you would require to interpret these theories, basically, right? So I hope that is clear. Any questions? So the way you'd start defining first order logic is to first fix the language that you want, right? So without the language, the rest doesn't make any sense. You need to specify what are the symbols, what are the function symbols, what are the relation symbols, what are the constant symbols, and so on. So that is what is meant by a first order language. Any questions?
Yes, I'm just curious, like, so we are saying first order here, right? So what is order specifically, and are there like other order languages also then?
Yeah, so there is what is called second order logic. There is first order logic, second order logic. Maybe I will mention that later, because once I define the syntax and semantics, maybe it's easier to understand. Is that okay?
All right.
Yeah. Any other questions? Okay, so let me quickly define the syntax. So the syntax is also slightly more convoluted than in the case of propositional logic. So the syntax is defined. So you want to define the syntax for the formulas, and these are defined over a first order language, right? So the first thing that you fix is a first order language, the symbols that you would want to use, right? And now you define the formulas over this language. Just as in the case of propositional logic, you need to define what are atomic formulas. For propositional logic, it was very simple. It was just propositions. And then you have the logical connectives, right? You have the Boolean connectives, not and negation and disjunction, and you have quantification. So that's it. Okay. So this is basically the recipe, right? So you have atomic formulas, and you have the logical connectives, and that's what defines the syntax of the logic, right? So the only extra thing that you have in the connectives is this quantification, right? Otherwise, it's just Boolean, right? But this atomic formulas becomes a bit more complicated because you have all these symbols floating around. Okay, so the way you define atomic formulas is to define first what are called terms, right? So what are terms? Okay, so you have this first order language. This is your language that you have fixed, and the set of terms is the smallest set satisfying the following conditions. So every constant symbol is a term, every variable is a term, and every application of a function symbol is also a term, right? So if you have a bunch of terms, and a function symbol with arity n, then you can apply the function on these terms, and that is also a term. Right. So again, it might look a bit complicated, but it's, I mean, just think of it this way. Constants are terms, constant symbols are terms, variables are terms, and function application, it's also a term. Fine. And these are the terms. These define terms. Okay. And using terms, you can define atomic formulas. What are atomic formulas? The application of a relation symbol, that is an atomic formula. If you have two terms, then the equality over terms, that's also an atomic formula. Okay? And that's it, right? So this equality, well, typically would include equality, but there are languages where you don't want equality. So if equality is there, then this is this is part of this is an atomic formula. Otherwise, it's not. Okay. So at the moment, I'm just including it. All right. So terms consist of constants, variables, and function applications. And atomic formulas, well, you take terms, and then you can also have a relation, application of relations, and this equality. Okay. Okay. Once you have this notion of terms and atomic formulas, then it's easy to define what are formulas. Again, you look at this. Let's go back to this recipe, right? So you have atomic formulas. This is what you want to define, and then you have these logical connectives. That's it. Okay. Okay, so what are formulas over the logic? Every atomic formula is a well-formed formula. If phi is a well-formed formula, then you can take negation. So this is just like in propositional logic. If so, you can have disjunction. That's also fine. And the only new thing in first order logic, as far as this this formula part is concerned, or the logical connectives are concerned, is you have quantification. Okay, you have something like this. So if phi is a well-formed formula, then I can write something like there exists x phi. X is a variable. Okay, the way you read it is there exists x phi. Fine. And the dual of this there exists is what is called the universal quantification, or for all. And so you can also write something like for all x phi. It need not be part of the syntax because it's a dual. It's defined as not there exists x not phi. Right. Okay, so this defines the syntax. Any questions? Again, we are not talking about the interpretation as yet. It's just syntax. When do you say that formula is a well-formed formula in first order logic? That's what I've tried to define. Right? Any questions? So at the very high level, it's not very difficult. The only additional logical connective that you have basically is this quantification. So you can quantify over variables in a formula. That's what it's saying, right? X is a variable, and you're allowed to quantify over variables in a formula. The other connectives are just Boolean connectives. And you have slightly more complicated notion of an atomic formula simply because you have all these functions, constants, and relations. So constants, variables, and functions are terms, and relation is an atomic formula along with equality. So that's basically it. Okay, so any questions?
I don't know if my question makes sense. I'm a bit confused. Like when we say Boolean logic, so is it a like kind of first order logic where we define like these terms and relations and all?
Yeah, so you can think of it that way. I mean, you can easily translate every propositional logic formula into a first order logic formula where you're not using quantification, right? So the language that you would use is what I defined here, right? So you don't have constant symbols, you don't have function symbols, you don't have equality, you only have relation symbols, which are the propositions. And
so
these are relation symbols.
Okay, sorry.
Sorry, yeah.
No, I mean when people use this word like Boolean logic, do they mean propositional logic?
Typically, yes.
Oh, okay, okay.
Yeah. Mm-hmm. So it's not first order that is meant. Yeah.
Because we don't have constant symbols and function symbols. That's why it's not a first order.
That and the fact that well, very importantly, you don't need quantification.
Okay.
Yeah, so when you write Boolean formulas or propositional logic formulas, you don't have the notion of quantification, which is allowed in first order logic.
Okay, so
Right?
okay.
So propositional logic is, you can see that it's easily, you can easily see that it's a fragment of first order logic, right?
Okay.
Yeah, so where your propositions are relation symbols, you don't have anything else, and then you simply have the Boolean connectives. Well, I mean, what I mean is you don't use the power of quantification.
Okay.
Yeah.
Thanks.
Okay. Any other questions? So just to give you some examples, right? So if X is a variable, then X is also a term, right? If plus is so if you think of that elementary number theory, the language associated with the elementary number theory that we just said, plus is a function, right? So I can apply plus on, and it's a binary, it has arity 2. So I can apply plus on 2 variables. So technically this is not the way to write it. I should, I mean, to be precise, I should write it like plus with arguments xy, right? But just so that it's easy to read, I'm just writing it this way, and I hope it's clear, right? X plus y. This is a term, and successor is a function, and therefore something like this. It's not a term because you're using equality, right? So again, I should probably just use this as for equality. So this is my equality. Yeah, it's not a term, but it's an atomic formula. Okay, so these are some simple examples. Fine. Any questions? Okay, so this we have defined the syntax, and now we should define the semantics. Now the semantics becomes a bit complicated to define because you have all this, all these additional terms going around, right? So what I'll try to do is just to give you an overview of the semantics, and we can come back to the formal definition if we need. But I will, instead of that, I will try to give you some examples so that it's easy to understand how to interpret these formulas. Of course, if you don't understand the examples, we can come back and look at the formal definition of the semantics, right? But what is the idea behind this? How do you define semantics, right? So you have an FO language, first order language, which specifies the symbols. So this specifies the symbols, right? Now you want to define an interpretation for these symbols, right? That's what that's where you start with, right? In propositional logic, how did you start? With a valuation. The valuation defined an interpretation for the atomic object, which is a proposition, right? So now here the atomic objects, well, there are many objects. You have relation symbols, you have function symbols, you have constant symbols, you have variables, and so on, right? So you have to start by giving an interpretation for these things, okay, or giving a meaning for these things, okay? So how do you do it? Well, the way to do it is to fix an underlying set. So this is the set over which you're going to interpret your formulas. And over the set, you fix an interpretation for each of the relation symbols, for each of the function symbols, for each of the constant symbols. So this is what is called a first order structure. Okay, so formally, what is a first order structure? You have to specify an underlying set, a set, and so this is a non-empty set. This is assumed to be a non-empty set, and you have, think of this as a function, tau as a function over the set of symbols of relation symbols, function symbols, and constant symbols, which gives an interpretation for these symbols. Okay, so you have an underlying set and a function which gives an interpretation for all these symbols into this underlying set, right? So for example, if I take a relation symbol R, right, with arity n, what is the interpretation of R? I mean, I need to say what this relation is, right? It's a relation. So what is this relation? It should be a subset of, the interpretation of that relation should be a subset of S to the n, right? Where S is the underlying set. N because that's the arity of the relation, right? Or if you take a function symbol f with arity n, how do I define the meaning of that function? Well, it has to be a map from S to the N to S, right? So it takes N parameters, the function takes N parameters and then returns a value, which is an element of the underlying set. Okay. So that's where you start. Okay, so you have an underlying set and you have an you kind of fix the meaning of all these symbols with respect to this underlying set, and this is what is called an else structure. Okay, and so that's what defines meaning for all these symbols, and you also have to define the meaning for the variables, right? That is what is called an interpretation, or sorry, it's an assignment. So for every variable, you define what is the meaning of that variable in terms of the underlying set. So all this is defined in terms of an underlying set. Okay, is that fine? Is that okay? Any questions at this point?
If you could summarize the hierarchy of all the concepts that we discussed so far, that would be helpful.
Can you be a bit more specific?
No,
part
so we have
is not clear?
we've defined so many things. So if you could just summarize how they all relate to each other and what is contained in what.
So is the syntax clear? Or you want me to go back to the syntax of the logic? Or
no, it's all clear. It's just putting them all into perspective would help.
I think I'm not sure whether he is asking this that so first order logic is the topper hierarchy and it contains this first propositional logic and numerical logic.
No, I didn't mean that. I meant I mean, we have defined so many things right now. Like this L structure seems to be something that we are defining with what we have defined before. So
okay, so no, this is where we are starting. So you have the syntax, which is separate, right? So I'm going to, and now I'm going to start. I want to start defining the semantics, the meaning of the formulas, right? How you interpret these formulas. Okay, and
right.
that is what is given by, that is what is specified by what is called an L structure. Fine.
Okay.
Okay, so this is the building. I mean, this is the first step. Okay. Okay, so what is an L structure? You basically have an underlying set. So you are interpreting everything based on an underlying set. It can be anything. I mean, it can be, let's say, set of real numbers, set of natural numbers, whatever, right? It depends on what you want to write formulas in. Okay. So that there is an underlying set, and you have a lot of these symbols, relation symbols, function symbols, constant symbols. You need to give an interpretation for all these symbols into the underlying set. So that is what is specified by an L structure. That's it. Is that okay?
Yes.
Okay. So for instance, I mean, constant symbol will be easiest, right? C is a symbol. It's just a symbol. What is the meaning of C? Well, it should be an element in the underlying set. Okay. So which is that element that is specified by the L structure? Is that okay?
Yeah, got it. Understood. Thanks.
Okay. So similarly, so relations and functions are slightly more complicated. Relations and functions have arities, which means it specifies how many parameters it takes. So if you look at a function, then it takes a bunch of parameters, let's say n parameters. Then what the L structure will tell you is how to interpret this function, right? What is the meaning of this function? So if it takes n parameters, then it is a function from S to the n, where S is the underlying set, to a value in the set S, right? Because it's a function, right? It has n parameters and it maps to a particular value in the underlying set. That's what it means. Okay. So an L structure is where you start. That gives you the meaning of the basic building blocks of the logic, and you also have these variables, and therefore, in order to assign meanings to variables, you have assignments, which is for every variable you specify what is the underlying, what is the value in the underlying domain. Okay, so let me just skip the rest of the formal definition of the semantics, maybe, and we can come back to this if we need. Let me give you some examples. Okay. Okay, so let's look at this, right? So how do you characterize, for instance, equivalence relation? So I have a symbol R, which is a relation symbol, and I want to write a bunch of formulas which characterize, which kind of insists that the way you interpret R is that R is a relation, R is an equivalence relation, right? Okay, so R is a relation symbol. So the arity of R, it's a binary relation symbol. So the arity of R is 2. And how do you define equivalence relation? Well, it is reflexive, it is symmetric, it's transitive, right? And this is how you write first order logic formulas to specify that. R is a relation symbol. It has arity 2. Okay, so it takes 2 arguments. To say that R is reflexive, you would say that for all variables x, R of xx holds. Okay, so what is this interpretation of for all here? It says for all values in the underlying domain, the relation is reflexive on the value. So that's what it means. Okay, so this quantification, you can think of it as quantification over the underlying domain, right? So you have some underlying set. So this is quantifying over all elements in the underlying set. All right. You can have a sequence of quantification. So for instance, something like this symmetry you would say that for all x, for all y, if x and y are related, then y and x are also related, right? So this will say that the relation is symmetric, correct? And how would you say that something is the relation is transitive? Well, you have 3 variables for all x, for all y, and for all z. If x and y are related, as well as, so if r of xy and r of yz, then r of xz, right? So that implies r of xz. That's the notion of that specifies transitivity, right? Now you take any model, basically any interpretation which satisfies all these 3 formulas. It imposes or it insists that the relation R is interpreted as a equivalence relation. So is this reasonably clear, or without going into the formal semantics of the logic, is this okay? Does this make sense?
Just to clarify, we are applying these relations on function symbols, right? Just by going by the definition of this sort of language.
No, so maybe the way I wrote it is a bit confusing, right? So R is a relation symbol. It's not a function symbol. Yeah, if you want, I can write it.
No, I mean the x and y, the symbols on which we are applying the relation. So they are function symbols.
No, so these are variables. Sorry, so x is a variable. So x is a variable, y is a variable, z is a variable. Okay. So these are variables, and how do you interpret variables? These are variables are mapped into elements of the underlying set. So it takes values. It takes it's just a value, right? So if your underlying set is a set of natural numbers, then x would take some number as a value. And when you write something like for all x, it's saying that for all numbers.
Okay.
So for all numbers, something holds. That's what it says.
Okay. Thanks.
Okay. Yeah. Any other question? Okay. Let me try to give you one more example. Slightly more complicated. The notion of strict linear order is something very standard in mathematics, right? So let's define, or let's kind of characterize strict linear order using first order formulas, right? So this less than is what I want to define. Less than on, let's say, natural numbers, right? I mean, this is a standard. It's a standard strict linear order, right? Okay, so how do we define less than? It's a relation, and it's a binary relation, which means that it has an arity of 2, right? So for it to be a strict linear order, it's irreflexive, it has to be transitive, and it has to satisfy the property that every two element is in the set is related, right? I mean, you can compare between any two elements, right? So a standard example of a strict linear order is the usual less than on natural numbers. So that is a strict linear order, right? Okay, so now let's say we have this symbol. So this is a relation symbol. I want to ensure that it is interpreted as a strict linear order. So I want to write a bunch of first order formulas which make sure that it is interpreted as a strict linear order, right? How do I do that? The first thing I want to say is it's not reflexive, right? So for all x, it is not the case that x is less than x. Again, because it's a relation, I'm writing it this way. But I mean, for you to be able to easily read, let's just look at this statement, right? For all x, it is not the case that x is strictly less than x. Okay, so that's the first statement that says that it's this relation symbol, it's not reflexive, right? And transitivity is the same that you had earlier. So this you would still have for all x, for all y, for all z. If it's the case that x is less than y and y is strictly less than z, then x is also less than z. Okay, so that's transitivity. And you have this notion that you can compare, right? So how do you specify that? For all x and for all y, it is either the case that x is less than y, or x and y are the same. So here is where I'm using equality. This is inherently part of the logic. And so it's either the case that x is less than y, or they are the same, or y is less than x. Okay, so this specifies that you take any two elements in the underlying set, you can compare between these two elements. Fine. Again, I hope this makes sense. If there are questions, please ask. Is this okay? Just a couple of more examples that hopefully that makes it clear. Suppose I have a formula of this form, right? This is an existential quantifier. It says that there is an element, right? So there exists x, there exists y, such that x and y are not the same. That's what this statement says. Yeah. So this formula insists that any structure or any model which satisfies this formula should have at least two distinct elements in the underlying set, right? So any model for this formula should have at least two elements in the underlying set. That's what this formula ensures. You can kind of generalize it to a slightly more sophisticated formula, which ensures that there are at least n elements in the underlying set. Okay. What about this formula? It says for all x, for all y, x and y are the same, right? It's the negation of this formula here, right? This says that there is at most one element in the underlying set, and we assume that the underlying set is not empty. So this basically says that there's exactly one element in the underlying set. Okay, so for any model of this formula, we'll ensure that there's exactly one element in the underlying set. So these are some examples of formulas. Is that okay? Any questions? Again, I'll share these slides so that you can go over it later. Any questions? Okay, so that defines the syntax and semantics of first order logic, and now we can ask the same sort of questions, right? What about the satisfiability problem in first order logic, right? Or the validity problem of first order logic? What about proof systems? Are there complete proof systems? So here I'll just make some list out some statements. Again, I'll give you reference at the end of the session. So this was shown by Gödel. This is what is called Gödel's completeness theorem. That there are proof systems, or there is a proof system which is sound and complete for first order logic. Okay, so you can have the same thing as the notion of derivability and semantics, right? So you can have a system where you can derive formulas and you can equate it to the notion of semantics. Okay, the notion of validity. What about the satisfiability problem itself? Well, the satisfiability problem and also the validity problem for first order logic is in general undecidable. So which means that there is no no algorithm exists. So it's not about complexity that you're talking about. There is no algorithm which can solve this problem. So that's what it means, right? And so here is an undecidability result. But then there are these solvers. These are called SMT solvers, which is basically deal with first order logic. Okay, so you start with SAT solvers, and SMT solvers are slightly more sophisticated, and they are also very fast. Where you get a lot of flexibility because you can write formulas or assertions which involve predicates, functions, constants, and so on. And they typically they also work well. They are pretty reasonably fast, right? So the underlying language that they're using is first order logic, and the general case, the satisfiability problem is undecidable. But what you can look at are restricted theories, right, where it is decidable. So let me give you some examples. The theory of integers. Okay, first order theory of integers. This is also called Prosperg or arithmetic. So what do we have? In the signature, you have these constants 0, 1. You have plus minus, which is your addition, subtraction. And you have this relation, which is less than or equal to. Okay. So it is a well-known result that satisfiability problem for this theory, the theory of first order logic on integers, it is decidable. And if you look at formulas which are quantifier free, so you don't have these quantifiers that exist for all, then it's actually NP complete. So it's it's quite attractive in that sense. Fine. So this is, I think, triply exponential if you don't have this restriction, but if you have this restriction, then it's already NP complete. Okay. So there are theories. First order logic in general is undecidable, but that does not mean that it's not interesting anymore. And clearly it is quite interesting because SMT solvers are very fast, and it allows you to use the power of first order logic. Typically, most of these solvers don't allow you to write quantifiers, but you still can use relations and other predicates, basically, right? Which makes it easier and more natural to write specifications. So if you take the first order theory of integers and you include multiplication into it, then it becomes undecidable. So if you don't have multiplication, you have only addition, subtraction, and the order relation, then it is decidable. Okay. So let me just give you one more example. For this, I'm doing a bit of hand waving, but I hope it will be reasonably clear. You can also have theories of, let's say, arrays or other data structures, right? So the signature, there are two relations, read and write. Again, I'm doing a bit of hand waving because I'm assuming that there is this theory of integers which is already built into ordering and stuff, right? And let's look at these three axioms. Okay, so these three axioms basically say the following. So A, I'm interpreting as an array, I an index, and V a value. So the first axiom says if you write the value V to the ith position in an array, and then you after the write, if you read the value in the ith position, it's going to be the same as V. All right, that's the first axiom. The second one says, well, if you look at the array and you have two indices I and j which are distinct, and so if I and j are distinct, then if you write the value V into the ith index of the array, and then after that you read the value at the jth index, then what you get is simply, well, whatever you get if you directly read the value at the jth index, right? Again, that's because these indices are different, right? So by writing into I, you don't change the value of j. That's what it's saying, right? And the third axiom basically says that if you have if you have two arrays A and B, and for all indices, if the values are the same in both the arrays, then these two arrays are the same. Okay? So these define some axioms. Basically, you can interpret as a theory which defines the theory of arrays. And you can ask for the satisfiability problem under this in this theory of arrays. It turns out to be undecidable. But the point is, if you look at the quantifier-free version of satisfiability problem, then it is decidable, and it is known to be NP complete. Right. So first order logic gives you a lot of power. It makes the decision procedures undecidable. So that means, well, theoretically, there's no decision procedure, right? But that does not really mean that it's uninteresting, because you have a lot of these fragments which are already interesting from the verification perspective, for which you can give decision procedures. And there are solvers which you can use. These are very fast. The language of first order logic kind of allows you to write specifications which are more natural, right? So it includes more sophisticated constructs like parameters and predicates into it. So one of the popular SMT solvers, it's this Z3 from Microsoft. So yeah, you should try it out if you're interested in this. Okay, so that's what I wanted to mention about first order logic. Are there any questions? So I want to do something slightly more, and which might be directly relevant to verification. At this point, any questions? Again, I hope I am audible. If I am, can you confirm that I'm audible?
Yes, you are, sir.
Sir, can you please re-explain the second axiom of theory of arrays?
Yeah, so it's basically saying that if you look at two indices, right? So you have an array A, and you look at two indices which are different, and if you write into one index, then the value of value on the other index doesn't change. That's basically what it's saying.
Okay, understood.
Is that okay?
Yes.
So this part, it's saying, well, you are writing into the index I, and then you're reading from a J, right? If you're doing that, then if I and J are different, then you might as well read from J directly. It's going to be the same value. That's what it's saying. Any other questions? Okay, so we started with propositional logic, which is just Boolean reasoning. The satisfiability problem is very interesting, and it's hard. And you have these SAS solvers which work very well. So that's a very kind of a good illustration of the fact that the worst case complexity, well, it doesn't mean that it's the end of the road, right? And so one of the main drawbacks with Boolean logic or propositional logic is the fact that you only have Boolean connectives, and you are basically reasoning about Booleans, and that can be extended in first order logic to include predicates and more sophisticated constructs. But the drawback being that the associated computational problems become more difficult, right? They're typically undecidable, but yeah, in general, more difficult, right? So what about the next thing they can think about is, well, what about logics which are specifically designed for a particular domain, right? Verifying a particular type of systems, Okay, so let me give you an example of kind of system that you might want to verify or prove correctness. These are called reactive systems, right? So what are reactive systems? These are not programs which are computing something. So it's not like a program which computes, let's say, a factorial, right, or the nth prime number. For these programs also you want to give correctness assertions, but these are not reactive systems. Reactive systems are systems which are basically kind of doing servicing, right? A simple example would be something like a coffee machine or coffee vending machine. You know, the machine is always running, it never stops, it's not computing anything, it's just waiting for someone to come and press a button, right? When someone presses a button, it produces some output, right? So if you press the button coffee, then hopefully it gives coffee. If you press tea, then maybe you get tea, hot water, whatever, right? So and so on, right? So it's not really computing anything, it's just waiting there for the user to come and give an input, and then it services that request, right? So that's basically what the coffee machine is doing, and that's the basic idea behind a reactive system. Okay, and it's not just coffee machine. For instance, you can think of the print server as a reactive system. It's not really computing anything, it's just waiting there, right, for people to send print requests, and then it prints. Well, it interfaces with a printer and then prints the document. Yeah. And if you think about it a bit more, then your operating system is also a reactive system, right? It's just waiting there for you to interact with it, and then it services your requests. Okay. So first order logic, well, you can write specifications in first order logic for all these reactive systems, but maybe you don't need so much of sophistication, right? So one of the important aspects of first order logic or these reactive systems is there is this notion of time, which is important, right? So for a coffee machine, you would want to have what are the kind of correctness assertions that you would want to make. For instance, you might say something like, if I request coffee, then eventually I get coffee. Yeah. Or if I give a sequence of requests, so I pressed the button T and immediately after that I pressed water. Well, you might want to say that it just ignores the second button, or you might want to say that well, it gives you the output in the correct sequence, right? It does not swap the sequence in some sense, right? So it's similar with print servers, right? Or in general for concurrent programs. So the typical kind of specification that you would want to write is something like, for instance, it's never the case that a process starts, which is not ready. So suppose start is a flag or a Boolean object. And so you want the process to start only when it's ready. It's not the case that it starts when it's not ready, right? Or you could say something like, if a request is raised, then it's eventually acknowledged, right? These are predicates. So request and acknowledgement, it's like these are like predicates. But this word here, eventually, it's something to do with time, right? So it's like the temporal flow of the system. Okay. Another specification you might want to say is a process is enabled infinitely often, right? So a process being enabled is a predicate, but this notion of infinitely often is something to do with time, right? It's a temporal aspect. Okay. Some property is eventually stable of the system. This property itself is a specification. But these words, eventually and stable, it's something to do with the temporal aspect of the system. Yeah. So if you want to make this kind of specifications, which make a lot of sense in concurrent programs, and especially involving such reactive systems, well, you could use first order logic, but you might be able to kind of get away with a more domain specific kind of a framework, right? And that is possible, and that's what is called a temporal logic. So it takes time, or this temporal evolution of a system as a building block, or that's the important aspect of this logic. And then you basically have Boolean connectives and logical operators which can specify the evolution of the system with respect to this temporal aspect. Okay, so let me just formally define the syntax, and then we look at more examples of what can be specified. Okay, so this is what is called a linear time temporal logic, and it's a very popular formalism to specify and verify systems. What is the syntax of LTL? You have a bunch of propositions, just as in the case of propositional logic. So it's a countable set of propositions, and then the syntax is, well, propositions are well-formed formulas. You have the Boolean connectives, negation and disjunction, and these are the two new operators, logical operators. Okay, so there is an O alpha. This is read as the next alpha. I'll tell you the interpretation in a minute. And this U here is typically read as until. So alpha until beta. Okay. Okay, so what about the semantics? Now we are talking about the temporal evolution of a system, right? It's not one single valuation, right? So you have, think of it as time steps, right? So you have the first clock tick where you have the system in some state, and then the second clock tick where the system might evolve, right? Things might change. Okay, so an abstraction of this is to simply think of a model as a sequence of valuations. Okay, so it is not one valuation, but a sequence of valuation. It's an infinite sequence of valuation because we are interested in reactive systems, right? These are systems which never terminate. Okay, so it is simply a sequence of valuations. So this part here is a valuation. This is what you had in propositional logic. And here you have a sequence of valuations. Okay, so it's a map from the set of integers to valuations. Is this okay? Is this definition of a model clear? I hope I'm audible. It's okay, right?
Yes, sir, you are audible.
Okay. So the syntax and the semantics. So the syntax is basically Boolean propositional logic along with two logical operators. And the semantics, the way you start with the semantics is in propositional logic, you have one variable, one valuation. Here you are interested in talking about the evolution of time. So you have a sequence of valuations, right? An infinite sequence of valuations. So that's the only difference. Okay, I hope that is fine. Okay, so then you talk about the satisfiability of a formula at a particular time instance of this model. Fine. So how do you define that? You have M, which is a model. You have I, which is a particular time instance, and we're going to say that Mi satisfies alpha. So alpha is satisfied by the model M at the time instance I. So that's the way you read it. Yeah. Okay, so how do you do that? Well, propositions are immediate, right? You have Mi satisfies P if P is in Mi. So this is an atomic object, right? Which is given. That's part of the model. Okay, and the Boolean connectives are also the same. I mean, just as you define for propositional logic. So there's no difference here. So the only difference or the only new thing is are these two operators, right? O and until. Okay, so how do you define O? So you have a model M, you have a time instance I. When you say that it satisfies next alpha, O is interpreted as next. Well, if in the next instant alpha is satisfied. Okay, so you have this timeline which is going. At each point you have a valuation. So all these involve a valuation. So here is where you're making the assertion next alpha. Next alpha holds at I if in the next instance, which is I plus 1, alpha holds. So that's the interpretation. Okay. What about this notion of until? Okay, so alpha until beta holds at instant I if there exists some point in the future where beta holds and everywhere in between alpha holds. Okay, so think of it, think of this picture, right? You have this timeline which is going, and at every point you have a valuation, right? We are making an assertion at this point I. So alpha until beta holds at this point. If there is some point in the future where beta holds, and everywhere in between alpha holds. Okay, so in some sense, alpha is invariant till you satisfy beta. That's what it says. All right. So there are a couple of derived connectives, and let me just define that, and I'll give you examples. Okay, so these are derived connectives which are useful. Diamond alpha, it basically talks about eventually a property being satisfied, right? So what that means is at time instant I, we say that diamond alpha holds if there is some point in the future, some k, which is in the future, where alpha holds. All right, so eventually alpha holds, that's what diamond says, right? Box alpha is the dual of this, this diamond. What does that say? Well, that says that it is always the case that alpha holds. Okay, so at time instant I, box alpha holds if for all instance in the future alpha holds. Okay, so let me give you some examples, and hopefully that will be clear. So let's just pull up the properties that we listed earlier, right? And now I can give you formulas in LTL which actually characterize those properties. Okay, so let's look at the first property, which says that it's never the case that a process starts but it is not ready. So how do you write it as a formula in LTL? So this box says it's always the case, right? So always the case what? It is the negation of this holds. The negation of what? The process has started and it is not ready, right? So this is the formula. Okay. How do you say that the second property? How do you say that if a request is raised, then it's eventually acknowledged? Well, it is always the case that if the process makes a request, then at some point in the future it is acknowledged. Okay. Here are a couple of interesting formulas. So you can say, if you want to say that a process is enabled infinitely often, how do you say that? Well, it is always the case that eventually the process is enabled, right? So box says that it is always the case. Always the case what? Always the case that this formula holds, diamond enabled, and diamond says that eventually it is enabled. Okay, so at every point, there is some point in the future where the process is enabled. That's what this formula says. Okay. If I swap these operators, these logical connectives, box and diamond, and if I say something like diamond box phi, then it means that phi is eventually stable, right? Phi is eventually a stable property of the system. So there is some point after which phi always holds. Yeah. So for instance, you might say that, okay, this process always deadlocks, right? So there is some initial prefix where it's fine. After that, it's always going to deadlock. Okay, so something like this is what you would write. Yeah. Is this reasonably clear? Are there any questions?
Here, do we have any kind of order relation in the formulas?
Can you repeat the question? Sorry.
I mean, do we have any kind of order relation among the formulas?
In the formula, no. In the interpretation, you have this timeline, basically, this temporal view of the model.
Okay, so can you just put the last slide?
Yeah.
So like in this, like alpha until beta, you're saying, so it holds for everything between I and j. So aren't we introducing some kind of order relation among the formulas?
No, this is the semantics, right? So alpha until beta, I mean alpha is any formula, beta is any formula. Yeah.
Okay.
This is the semantics. So you have this timeline. This is the interpretation of the timeline, right?
Mm-hmm. Okay.
So you're making an assertion at the instant I, at the time instant I.
Okay.
So you say that alpha until beta holds at I. If sometime in the future, there is some point in the future where beta holds.
Okay.
Okay. And everywhere in between alpha. So there's no real order between alpha and beta. I mean, these are just arbitrary formulas, right? But in the interpretation, because you have this timeline, you're saying that, well, alpha continues to hold till beta holds. So let me give you an example, right? So suppose this natural property you would want to say is that a process stays. So if it raises a request, then it stays in that request state till a resource is granted, right?
Okay.
So that you would write something like this: I'll request until grant. Yeah.
Okay.
You would say box of that because you want to say that at every point that holds, right? So if a process makes a request, then it stays in that request state till the resource is granted. So the grant comes sometime in the future, and till that point, it stays in this request state. So that might be a property that you want to write.
Okay. So in the semantics, we have an order, but in the syntax itself, there is no order relation.
No, there is no order in the syntax. It's just these two operators. So you can talk about the next step, what happens in the next step, and you can talk about what happens eventually.
Okay, so those are semantics, like eventually and next step.
Yeah, so those are the two.
Okay. So can we say that even the statement like a process stays in request state till resources, right? This is also a syntax, like can we sorry, a semantics, can we say that?
Say it again, which one?
Like this statement itself. Can we say in some way say that it's also a semantic interpretation of the syntax?
Yeah. So the what I've written here is the semantic interpretation in English, right? I mean, of this.
Yeah. So we do say it as semantic. No, I'm just asking that we do call it semantic interpretation, right?
Yeah. So this is just, I mean, I've written it just for you to understand. Of course, that's not the formal semantics. Yeah. The formal semantics is in terms of these models.
Okay.
I mean, these are probably your specifications, and these specifications correspond to such a formula in LTL.
Okay. Okay. Thanks. Thank you.
Any other questions? Okay. So what is the notion of satisfiability here? Well, a formula is satisfiable. When you say that a formula is satisfiable, if there exists a model, there exists a time instant when such that mi satisfies alpha, right? So the notion of satisfaction depends on the model and a time instance. Okay, so this is the notion of satisfiability, but again, it's quite easy. Right, I'm not saying anything about the past. Okay, so I'm saying about next step, eventually something happens and so on. It's quite easy to see that you can equivalently define satisfiability as there exists a model where it is satisfied at the first time step. So M0 satisfies alpha. Okay, so this is something that is straightforward. Okay, so this is the satisfiability question. Is this okay? Is this definition clear? So basically, is there a model which satisfies the formula? But here it's slightly more complicated because you have this temporal view. And so what you're asking is there a model and a time instance where the formula is satisfied?
Could you explain why it is equivalent, like why the time doesn't matter?
Yeah, so because, I mean, this is not a formal proof. So because these, so what are the two operators I have? I have O and I have until. Yeah. And this is only looking into the future and not the past. So I can write an equivalent formula which is basically holding at the initial point. But I mean, if it's difficult to see, forget it's fine. Just forget about that comment. You can go with this definition also for the moment.
Okay, so you are saying that we can kind of shift the model such that it happens at a time in the future.
Correct.
Okay.
Correct. Yeah, that's basically it. Okay, so so this is the problem that we want to address. But is the syntax in semantics clear? The notion of satisfiability. So other than the fact that LTL is widely used, the reason I want to discuss this is because of a interesting technique which is applied in order to solve this problem. So any questions at this point? So I will probably, yeah, there's a question.
LTL is also undecidable, right?
What of LTL is undecidable?
Okay, satisfiability.
That is what I will address in a minute.
Okay.
Yeah. Any other questions? Okay, so I will probably take another 10 minutes. Is that okay, Subhajit? Or
Yes, sir, sure.
okay. Okay, so there is, so the satisfiability problem is not undecidable, it is decidable, and there's a very interesting technique by which you show satisfiability, which is to go through what is called automata theory, right? Again, this is probably something that you have seen in basic BTech courses, theory of computation, right? Automata is, you view it as a formal model of computation, and the standard thing that you see is what is called a finite automata, right? What is a finite automata? You have a bunch of states, you have an alphabet, you have a transition relation function, whatever, right? You have an initial state and you have a bunch of final states. Yeah. So what's the idea behind an automaton? You have an input word over the symbols. It's a finite word, right? And you run the automaton over this word, right? When you run the automaton over this word, what you get is a sequence of states, right? And when you say that the word is accepted by the automaton, if, well, you look at the run of the word on the automaton, if it ends up in a final state, then you accept the word, right? I hope this is clear. I mean, I'm not explaining it in too much of detail. If someone wants me to explain, please let me know, but I'm just assuming that you've seen automata. Is this okay with everyone? Can someone confirm that is okay?
Yes.
Most of you have seen automata, right? This is just a plain finite state automata. There's nothing fancy here. Yeah. Okay. So finite state automata, you think of it as running over finite words. Now, in a reactive system, the system never stops, right? So the run of the system is not a finite word anymore. Okay. So what you have is an infinite sequence, right? It's not a finite sequence; it's an infinite sequence. So what you can do is kind of extend the notion of a finite state automaton to an automaton model, which either accepts or rejects infinite words, not just finite words. Okay, so these are what are called finite automata over infinite words. So the automaton model is still finite, which means the set of states are still finite. But the words that they are processing, these are infinite words, not finite words. Okay, so the basic components remain the same. You have the set of states, which is a finite set. You have a transition function or a relation, and you have a set of initial states. Okay, so this is it's pretty much the same, right? Now, what is different? Well, you have an infinite word rather than a finite word. Okay, so you have an infinite word over sigma, and you run the automaton over this infinite word, you get a run of the automaton. That part is also the same. Okay, now the question is, how do you accept? Because in a finite automaton, how do you accept? Well, at the end of the word, if you have reached a final accepting state, then you accept, right? But now there is no end of the word because it's an infinite word. Okay, so that is the only main difference between automata, the standard automata that you see, and the finite state automata that I want to discuss. All right. So the question is, how do you accept? Okay. So is that clear? So in a standard automaton, how do you accept? Well, you finish reading the word, processing the word. If you reach a final state, you accept. Now, for infinite words, you have an infinite word, right? So you don't really stop, right? So the question is, how do you accept? Okay. So there is a class of automata. These are called Buki automata. which defines acceptance as follows, right? So Bookie automaton is a pair of this form where A is an underlying automaton. This is a standard automaton, and you have G, which is a subset of the set of states. Okay, so you think of it as a set of good states, right? So B accepts an input word, which is an infinite word, if you look at the run of B on the word. So let's think of the run as, let's denote the run as a row. Again, a row is an infinite sequence, right? You look at the states which occur infinitely often in the run. You intersect with G that is not empty. So that's basically saying that there is, so you accept a word, an infinite word, the automaton accepts an infinite word if there is some run along which a good state occurs infinitely often. Okay, so what is a Bookie automaton? It's a standard automaton along with a set of good states, and you accept a run. So this automaton accepts a word if there is some run along which infinitely often good states occur. Is that clear? So let me maybe in terms of a picture, this is how it looks like, right? So you have an initial state of the automaton, you have a word, and the run of the automaton is, well, you have some prefix, and then it hits a good state. It can be one state, it can be a set of states, right? And basically then you have these loops. You can go away from the good state, but then you keep coming back. Okay, if that's the case, then you accept such a word. Okay, so that's the notion of acceptance, right? And the language of the automaton is the same as what you have earlier. It's a set of all words accepted by the automaton. The only difference is the word is not a finite word anymore. It's a set of infinite words. Okay, is that okay? So let me give you an example. So hopefully that will be clear. Let's look at the alphabet set where you have two symbols A and B, right? And consider the language which consists of all infinite words over sigma with infinitely many occurrences of A. So this is the set I want to accept. Okay, what would be the Bookie automaton which accepts this set? So here is a Bookie automaton which accepts the set. So let's just see why. Q0, this is the initial state. Okay, this is also a good state. It's not a final state, it's a good state, right? So if you see an A, you stay in this state. If you see a B, you go to a new state, Q1, and you keep looping on that new second state Q1 as long as you see a B. And the moment you see an A, you come back. Okay, so if you infinitely see A's, then infinitely often you will be visiting the state Q0, right? And therefore you accept that word. So that's basically the idea. Okay, is this okay? Is this clear? Any questions?
We don't encode. We don't have to care about finite words, right? Like, so we are assuming we're only gonna.
Yeah. So yeah, for the moment, let's not care about finite words. It's only infinite words. Yeah.
Right. Okay.
Yeah. Okay.
So, sir, it is not necessary that good state are always a final state, right?
So there's no notion of final state. It's only a notion of good state, right? Final state is for the standard automaton that you saw. So you only have good states. So the interpretation of good states is that the run has to infinitely often visit a good state. So it can be a set of states, right? So any state in that set is fine.
Okay, sir. Thank you.
Yeah. So there's no notion. I mean, final doesn't make much sense here because the word is infinite, right? There is nothing final. Yeah. So you just keep going through states. So if you infinitely often keep coming back to some good state, then you accept the word. That's what it says. Okay. Okay.
Yes,
So
sir,
let's
yes,
look
sir.
at the
But
Yeah,
at what point do you decide to accept?
Yeah, so I mean, let's not. So in order to define the language, I mean, there's no. You don't have to decide at some point, right? I mean, as a definition, it makes sense. Is that okay?
Okay, so it's like,
Yeah. So there is a decision question. So decision problems are a different matter.
Hmm.
So I'll come back to that in a minute. right? In terms of definition of the language of an automaton, it makes sense, right? I mean, you don't have to really take a time instance where you decide whether to accept or not, right?
Yeah,
You
that
have an
makes
infinite word. The run of the automaton is again an infinite word, but now you have states, right? Infinite sequence of states. In that infinite sequence of states, if there are infinitely often you see good states, then you accept. That's it. That's the definition.
Okay.
Okay. Okay, so now let's just quickly look at the complement of this language, right? Complement of this set. What is that? What is the complement? All infinite words over sigma with finitely many a's, right? Here you had infinitely many a's, but then now you want finitely many a's, right? Can I give a bookie automaton which accepts this set? Well, I can. So what I do is start with this Q0 and I keep looping on Q0 on both A and B. Yeah. And at some point I decide, or the automaton guesses that, okay, I'm not going to see any more A's because it wants to accept only finitely many A's, right? So at some point it's going to guess that I'm not going to see any more A's. So that's a B on which it changes state to Q1. And then here you have a loop only on B. So you see that this is an intrinsically non-deterministic automaton, right? It's not a deterministic automaton. This, on the other hand, was deterministic automaton. Fine. Again, I hope it's pretty clear that the language is the complement of this set. But the important point here is it's a non-deterministic automaton. And in the classic case, you know that non-determinism is irrelevant, right? I mean, it does not really add any power. You have the subset construction, which I am sure you would all see, right? In the case of Bookie automata, that's not the case. Okay, so non-deterministic Bookie automata are strictly more powerful than deterministic Bookie automata. So if I define acceptance in this manner, then non-determinism does make a difference. So this is an example of a language which cannot be defined using deterministic Bookie automata. Okay. Okay, so why? So this is like a crash course to automata on infinite words. But later, I think when Supratik gives his lecture, he will also come back to this. Bookie automata is just one model because there's no canonical definition, right? So there can be other definitions of acceptance, and then there are other automata models, which and some of which he will discuss in his lecture. What is interesting for us at this point about this automated model is this following this correspondence between LTL and Bookie automata. What is shown, or what you can show, is you can kind of translate the satisfiability problem of LTL into the emptiness problem of a Bookie automata. Okay, so formally, what does that mean? Given an LTL formula alpha, what I can do is construct a Bookie automaton B alpha. Okay, from this formula, I can construct an automaton, a Bookie automaton, such that the model so M is an element of the language of this Bookie automaton, or in other words, M is accepted by this Bookie automaton if and only if M is also a model of the formula. Okay, so given a formula, I can construct a Bookie automaton such that every word accepted by the Bookie automaton is also a model of the formula. So that's basically what it says. Okay. Now, what does that mean? Well, checking for the satisfiability of a formula, an LTL formula, is equivalent to checking for the emptiness of this automaton, right? You start with alpha. I want to check if alpha is satisfiable. What do? I construct this Bookie automaton B alpha. And then I check if the language of this automaton is empty. If it is not empty, then I know that alpha is satisfiable because whatever is the word, it's a model for the formula. Right? And if it's empty, then alpha is not satisfiable. Okay. Now it can also be shown that the emptiness problem for Bookie automata, it can be decided in polynomial time, basically on the structure of the automata. Okay. So therefore, using this translation or using this correspondence, we can give a decision procedure for LTL, which is first to construct this automaton and check for the emptiness of the automaton. So that's the decision procedure. Again, worst case complexity is not so great because this translation from formula to the automaton is an exponential translation, exponential in the size of the formula. Okay, so it's not about model, but the size of the formula. Right? So satisfiability problem itself can be solved in exponential in the size of the formula. That's what it says. Okay. So the model checking question. So let me not get into this. So here is a lower bound. This is a result. So both the satisfiability and the model checking question of LTL is these are both p-space complete. This was shown in this paper. But what is interesting is so we have these operators, right? Next and diamond. So if you look at the logic which only consists of either next or it consists of only diamond, then you can solve the satisfiability problem. So the satisfiability problem is NP complete. If you allow both, then it becomes P space. Okay, so that is something that they showed. Again, it is P space, but there are a lot of these tools which does LTL verification. Many of them are very fast. So in practice, it is quite reasonable to verify using LTL specifications. So I will stop here because I'm pretty much run out of time. Of course, if you have questions, I'll be happy to answer. And let me just give you some references for what I talked about. So here are some references. Okay. So the logic part, the initial logic part, you can pick up any book, but here are a couple of books which are reasonably easy to read. And this book by Huth and Ryan, it covers the proof systems that I was discussing. It also covers temporal logic, LTL, and also the branching time temporal logics. There are also a couple of few nice lecture notes and papers. So there is this lecture notes by Madhavan Mukund and Suresh from CMI, which you can download from their website, which has a nice introduction to both propositional logic, first order logic, and some sort of modal logics. For automata on infinite objects, you have this nice survey by Wolfgang Thomas, which is available. And there's also this entire volume of lecture notes in computer science, volume 2500, which deals about verification, various sorts of questions related to verification from the theoretical perspective. So some of this actually Supratik might cover in his lectures later. Yeah, so these are some references. If you have any questions, I'll be happy to answer. And I'll also share these slides.